Okay, so this talk is inspired by a question that Florian asked at the reception we had some time ago. And that is, how do you resolve all the scales in your supernova simulation? And we had a nice discussion about it, but it was quite a bit of wine, so I'm not sure how much of it stuck. And I thought giving an actual talk about it would be fun. So the first, about a third of this is a little astronomy to explain what supernovae are and why they're interesting and that sort of stuff. Then I'm going to talk about the physics of a particular class of supernova, the thermonuclear case. And then I'm going to show the tools that we put together to model the physics on scales that we can't resolve in the simulation. And I'm getting ahead of myself because I've got an outline coming up. But there's a lot of vocabulary, both the physics and the astronomy, and then some of the simulational stuff, so don't be the least bit shy with questions. And I'm looking at Lynn in particular. So this is a supernova 1994D in the galaxy NGC 4526. And that stands for New General Catalog Entry Number 4526. Astronomers have these wonderful names for things. And that's something like 55 million light years away, and this thing is about 200,000 light years across. It's a fairly big galaxy. Well, we put the telescope on it and saw something very bright in the outskirts of it. And this is a thermonuclear supernova, 1994D it is, meaning the fourth one observed in 1994. And a supernova is a very bright stellar explosion. The brightness rivals, but doesn't exceed, all of the light from all of the stars in this galaxy. So literally, a long time ago, in a distant galaxy, far, far away, a star blew up. And that's what we're going after. So as I mentioned, I'll say a little bit about supernovae and astronomy, and then I'll talk about this thermonuclear case, and in particular the single degenerate model. And degenerate is the state of the matter, meaning that it's the pressure due to electrons being so close together that they don't want to get to know each other because of the exclusion principle. We say that's degenerate. I'll go through a lot of the physics so people can get a nap, and then I'll talk about our numerical methods of how we resolve these things. Okay, so a supernova is the explosive death of a star. They occur something like 30 times per second in the observable universe. And we think they occur about every 50 to 100 years in our galaxy. Now, we don't always see them. And this thing right here with the exciting name G1.9 plus 0.3 is a supernova remnant for a supernova that we think went off about 110 years ago. And in red, or in blue here, is a radio image that was taken something like 2000, or like right about 2000. And then in the orange is an X-ray image that was taken about 15 years later. And what you see is that this thing is expanding, and it's expanding fairly rapidly. Now, we think that this thing was a star that blew up about 110 years ago, as I said, but it was toward the center of our galaxy and obscured by dust. And if we go back to this lenticular galaxy, now our galaxy looks different than this. It's a disk, but you see this dust and stuff. If you imagine that we are here and we look into the galaxy, there's material that obscures it, but the X-rays and the radio can get through and we can see it. So we think that that would have been observed if it had not been where it was. And that's an example of a discovery of a remnant. Now, about 80% of the supernovae that we see in the galaxy today are core collapse, and about 20% are thermonuclear. The core collapse is the death of a massive star when the core fuses to iron. It's no longer producing energy. It can't support itself. That degeneracy pressure I mentioned can't support it once you get a certain mass, and it collapses to form a neutron star or a black hole. And in so doing, some magic happens and the star blows up. And that's the subject of many, many talks because we can't robustly make that work. That's not what I'm talking about today. What I'm talking about is a thermonuclear case where a explosive thermonuclear reaction incinerates a star. So every now and then, we look up at the night sky and we see a new star. So this is the constellation of Aquila, the eagle, and if you go back to the mythology, I believe the eagle caught the thunderbolts of Zeus. But anyway, all of a sudden there's a new star in this constellation. This was observed in 1999, and this was I believe an amateur's photograph, but anybody could see it at the time. And it was something that brightened up to about 70,000 times the luminosity of the sun. Obviously, it's at a much larger distance, but suddenly there was a new star there. Nova is new in Latin, so we say these things in Latin to make them sound cool. And that is actually something called a classical nova, which is another type of explosion that I'm not going to talk about, but we typically see about 10 of those in our galaxy per year. Now, when we look further and go into other galaxies, we can also see similar things like that 1994D. And here is a simulated explosion of a supernova in another galaxy. You've got this bright point here that climbs up. This is the light curve, and you can think the total luminosity versus time. And it gets very bright in a few days. This is a scale of a couple of months maybe along here. And then it declines over days or weeks. And of course, we can put the spectrometer on the telescope and see the colors of the light, and then from that infer the elements. Now notice the shape of this thing. We'll come back to that. So a nova is a new star, and a supernova is a super duper nova that got the super when we realized that these things were going off in other galaxies and were bright enough to be seen. And again, they are a bright explosion of a single star that for a little while rivals, not succeeds, but rivals all of the rest of the light from the stars in there. Okay, so the observers have a taxonomy for the names of these things, and this is a busy slide. Don't worry, there won't be a quiz. But I wanted to give you a handle on how these are designated. So if you look at the early spectrum, if you don't see hydrogen, you're a type 1 supernova. If you do, you're a type 2. If you don't see hydrogen, but you see a certain silicon feature, then you're a type 1a. If you don't see that silicon feature, then depending on how much helium you see, you're a 1c or a 1b. Over here, if you see hydrogen and a lot of helium, then you're a 2b. And if you see mostly just the hydrogen, then you're a normal. And depending on what the light curve looks like, whether it's linear or a plateau, you can have these designations of a type 2L or P. Whole bunch of stuff for the observers to work out. The one we're interested in is the type 1A. And that's because it is the thermonuclear case. All of the rest of them are the core collapse. So 1B, 1C, all type 2, that's that core collapse of a massive star. Thermonuclear is the type 1. So much easier to think about it like a theorist, which is a preferable thing, that it's thermonuclear versus core collapse. And again, I'm talking about the thermonuclear. Now, one of the questions that often comes up is, well, what about a black hole or a neutron star? And that does not happen in this thermonuclear case. So if you hear about a black hole being created in a supernova, you know it wasn't the 1A. I think, I'm looking at Doug and Lupe, it wasn't Jim talking about there being an observation of a compact object in 87A that
not a compact object, but a hot dust cloud.
a hot dust
That might
cloud
be indicative of a compact
that would
object.
infer, okay. So one of the things is we look at these after and see if we see a hot cloud that would, or a compact object. So the thermonuclear case are bright. The brightness rivals that of a host galaxy, and that's something like 10 to the 43 ergs per second. And yes, we use these ancient energy units because they don't change. And the stars have been pondered for quite some time. The key is that they produce radioactive nickel-56, and it's the radioactive decay of that. The nickel-56 decays to cobalt-56 and then to iron-56 over the period of days or weeks, and that's what powers the light curve that you see. They occur less frequently than the core collapse that I mentioned. There's no compact remnant. And what's really critical is that the light curves are robust. And they have this unique relationship that follows from the fact that nickel-56 provides the light, but it also serves as a source of opacity, trapping the light. So these are light curves, and again, just think the amount of light coming out versus time. 0, we start the clock, these are days going along here. And brighter is, in this direction, a larger negative number. That's the way magnitudes work, but just trust me on that. And what you'll notice is that the decline is steeper for the dimmer ones. And that's a one parameter function, we call it a stretch factor, that allows you to calibrate these things and have objects of a uniform brightness. In astronomy, we call such things standard candles, and we can measure distances with that. Because if you know how bright something is, you put the telescope on it and see how much light you see from it, then you know how far away it is. And the likely event is the thermonuclear runaway occurring in a carbon-oxygen white dwarf. So just to show you the idea of a standard candle, you've got the supernova going off, you have an idea of how bright it is, so how bright it seems gives you the distance. A point source has an inverse square law. And with that, you can measure cosmological distances, and that means some of the largest distances in the universe. Doug, you're looking skeptical. No, all good, okay. Doing that in the late 90s, we realized something really, really bizarre. So back in ancient days when I was a student, we had 3 pictures for the cosmology. This is time flowing this way, the present, the past, the future. And we used to think that the universe, we know it is, velocities are receding, so we know the universe is expanding everywhere. But we used to think if there was enough mass, like say if neutrinos had mass, then gravity could win, the universe would expand a while and then collapse into a big crunch. And that might lead to another Big Bang. The Big Bang is what we call the origin. So that was the universe, Big Bang, Big Crunch, maybe a Big Bang, another Big Crunch, the bang, bang, bang theory. Or the universe might go out and just kind of slow down, or it might go out and just continue to slow down and essentially come to rest, I think the argument was, if it doesn't go this way. Or it might just continue to expand forever. Well, using these supernovae, people realized that the expansion is accelerating. And that's an extremely bizarre result. That's as weird as if you threw a tennis ball in the air and it came back down. You threw it a little further, it came back down, but you threw it so far and suddenly it shot off somewhere. And we now believe that something like 70% of the universe is this mysterious dark energy that we really don't know anything about. And I don't want to make fun of people, but you'll occasionally hear talks, particularly in high energy physics, where they're trying to constrain the equation of state of dark energy, which is a fancy way of saying we don't know anything about it. But that led to a change in our cosmology, that the universe is both a little bit older and evolving differently. And it came from using these things as standard candles, and that is very widely accepted, and the Nobel Prize was awarded. So here's a cosmological diagram where this is redshift. The simplest way to think about that is when something's expanding away from you, the light is shifted to the red. It's a little different on cosmological scales, but you can think of it as a measure of age, which is also distance. The supernova data, this is brightness versus this redshift, best match the cosmology that in this case is about 75% dark energy. These things are dimmer than in the universe without the dark energy, which implies that it has expanded more than we thought, which implies the acceleration question.
So is the evidence for dark energy, is this the only evidence, or is this the best evidence, or?
So the cosmologist might say that there's a lot of other evidence. You can get a similar cosmological picture out of things like the cosmic microwave background and stuff like this. But this was certainly the firstest with the mostest in establishing that. And
is that also galaxy size? It's actually constrained by...
Well, so there's large scale structure and galaxy size, and that's constrained by evolution as well. And that's what I mean.
Okay.
When you look at the cosmic microwave background, that is light from the original Big Bang that has redshifted all the way to the microwave. And you can get a handle on the early structure, and that kind of is used to put together models like this. But to this day, I believe it is fair to say that these standard candle supernovae are the best distance indicators, and that's the check on the cosmological models. Okay, so if we subtract off a uniform expansion, then we can make the plot look like this, which is basically just taking the blue curve, taking it away. Here's a piece of it. And what you notice is that the supernova data are noisy, and we refer to this scatter about the expansion as the Hubble residual, after the astronomer Edward Hubble, who discovered the expansion. And the question is, what is the nature of this scatter? What is the intrinsic scatter? And to understand that, we have to control systematic effects, like the role of dust in the galaxy that might change the observation that we see, or as a galaxy ages, stars go through their lives, they create heavy elements. Everything that was made in the Big Bang is hydrogen, helium, and a smattering of lithium. Everything else was made in a star and then blown up. The iron in our hemoglobin, the calcium in our bones, and that feeds back onto the explosions, because if you have a metal-rich white dwarf, the thermonuclear burning is different. And just to go one step further, 2 summers ago, we had our mock REU, and I had an undergrad that ran some simulations with a new class of white dwarfs that had improved stellar evolution going into them to see how they compare. And that's the type of thing that we look for, is an old white dwarf versus a new. That might be a systematic effect on the brightness. We want to control that and then measure the intrinsic scatter, because that's the big uncertainty in the cosmological observations. So if we want to know for sure the expansion history of the universe very precisely, then we have to control that. Okay, so over recorded history, there have been a fair amount of galactic supernovae. Now, by galactic, I mean in our galaxy. These things occur something like 3 times a second in the observable universe, but only every 50 to 100 years. There was one observed in 175 or 185, and something called RCW 86 is a remnant. There was one in 393, 1006, 1054, 1187, and then these 2 are considered the first modern observations, and that's modern on an astronomy timescale, that Tycho and Kepler saw them in 1572 and 1604. And then there was a shortage until 87A in the Magellanic Clouds, which is, I guess, was it the Large Magellanic Cloud? Yeah. The Magellanic Clouds are a satellite galaxy that's nearby, so this was the closest thing we had to a galactic supernova that we were able to see. So we can ponder these things from the point of view of looking at the remnants. And this is the remnant that we think was from supernova 185. These are 2 X-ray images where it's obviously a false color. We can't see X-rays, but the energy of the X-rays set the color scale, and the blue is the higher energy. This is the XMM satellite showing the full field, and then the Chandra. This was one of its first images where you can see the high resolution close-up of this. This, I got some notes here, I'll just give you a feel for it. This is something like 8,200 light years away, which is fairly close to us in the galaxy. And it's probably going to be about, I don't know, tens of light years across. It's been expanding for some time. Let's see. I wrote down some, don't hold me to that across. I wrote down some stuff about it. Here's another one, and this is the remnant from the supernova in 1006. And here, you see that there's this blue over here, which indicates high energy X-rays. Now, these things are expanding out into the interstellar medium that you can't see in X-rays because it's fairly cool. And the shocks heat up. And so this says there's a preferential direction for the expansion. And Professor Swesty and I and others were going to study these things in great detail, but the DOE did not have the wisdom to fund us for that. But this unstable growth and how it interacts with the interstellar medium is a very interesting thing. Here's Kepler supernova. This is something like 13,000 light years away. And here is a nice high-resolution image of Tycho's again. You can see it's experiencing a radiating shock, and it's expanding out, and that shock is unstable. And we're going to come back to some of that, a little bit of that physics. Questions on anything so far? I don't see anybody napping, so maybe I'm getting
What's emitting X-rays? For this law?
It's expanding at a high speed into a medium, and so it develops a shock, and it literally is hot enough to emit X-rays. Now, there's some other mechanisms.
For this many years?
Yeah. There are other mechanisms doing things, but this is basically shock heating.
Is there any star nearby that can actually, if it explodes, can kill us all?
So, that is a good question, and the answer is maybe. Okay. Serious work has been done on the kill radius for one of these things, and I don't think that we're within the kill radius for a traditional supernova. I think the closest one, and I'm looking at these two who might know some astronomy as well, the closest one is Betelgeuse in Orion's shoulder, and that's predicted to go supernova fairly soon. Now that's fairly soon on an astronomy timescale.
It will just this huge star.
It'll be a bright outburst that you could see during the day, and if you look at it, I've heard you could burn your eyes because it'll have a lot of X-rays and UV that you can get through. Now, the thing that some people argue could get us is something called a gamma ray burst, where there's a beaming to it, and there's apparently a star that they think might happen. Now, this may also be driving ratings up on some of these science networks, but if you're looking down the barrel of that might get us. But to my knowledge, and I'm looking at these two, we're not in the kill radius of a star that we think is going to go supernova anytime soon. That's what I'm aware of. Even Betelgeuse. Yeah.
So nova means new,
Right.
but supernova means the death of the star.
So-
So why death is new?
So the super part came when we realized that we were seeing these things in other galaxies, which are very, very, like millions of light years away. So it has to be far, far brighter than the nova that we saw, that's all. And now we understand that it's the explosive death of a
Oh,
star.
they did not know.
They did not know that.
Okay. Also, you said every every second there are 30 explosions, but we are only finding like 10 every year.
No, so we're finding a lot more now. Because of the interest in cosmology, we're now finding hundreds, if not thousands a year, and that's going to go up. They're building this large synoptic survey telescope that Brookhaven is actually building the CCD for, and that's going to scan the whole sky every few days and catch lots of these things. So in 1994, it was A, B, C, D, and so on, but now they can go through the alphabet multiple times and stuff like that. Observational campaigns are getting lots of these things.
How do you know the star is ready to blow?
So that's a good question. And the answer is that when I say that, I'm really talking about the core collapse case where you have a massive star and you can look at them and from the conditions infer that if they're getting close, there's several objects that have had outbursts that we think are getting ready to go. But also, the very massive stars don't live very long. So if you are near a massive star and you can look at it and tell it's getting close to the end of its life, you know what's coming. The very bright stars, they live fast and die young. So literally, I mean, I think the most massive stars can barely make it to millions of years. So if you see a star like that, relative to other things, you know it's going to be coming, and then toward the end of their lives, they expand and some make outbursts. Okay, so what are these things? Well, the discovery, in air quotes, by Tycho. Discovery is a strong word because anybody who looked up could have seen the thing, but he wrote it down, Nova Stella, and that's that funny looking FS thing that they used to do. And again, writing it in Latin makes it look cool. And this I is this thing here. And so without using telescopes, just using naked eye observations, he kept detailed records. And an astronomer, Pilar Ruiz Lapuente, was able to reconstruct a light curve from this thing, and it looks like a type 1a supernova light curve. So he was the first to record, and that's why we call it a modern observation. And the question becomes, what exactly are these things? Now, I mentioned the massive star. This is the other case. And there are three ways that we are exploring to do that. There's the so-called single degenerate Chandrasekhar mass. A white dwarf is a compact star. It's degenerate because the electron's not wanting to get too close, gives the pressure. And it can only get so big, and the Indian astrophysicist Subrahman Chandrasekhar figured this out on a boat trip from India to England in the 30s. It can only get so big before gravity will cause it to collapse, and the electrons will lose the battle, and then it can explode as that happens. It doesn't collapse, but it can explode as that happens. And what happens in this picture is you've got a white dwarf that's part of a companion with another star. The other star, toward the end of its life, puffs up. We know it's an old star, though it doesn't have to be. It could be a regular star that got close. And matter falls on this white dwarf, compressing and heating it. Just as it's getting ready to collapse, it explodes. You could also have a pair of merging white dwarfs, and that is two of these compact stars will merge together into one object that explodes. And Lupe is going to answer that question for her dissertation. Or at least he's on the way to it. And the other case is you could have a so-called sub-Chandrasekhar, which is this picture here. But in this case, if you're accreting helium, and the star would look a little different, that can ignite on the surface and trigger a detonation below. So the question is, which of these pictures involving the compact star known as a white dwarf can blow up in a supernova? So the one I'm going to focus on is this, the single degenerate case. And I'll step through the stellar evolution of that. So imagine that you have two stars together as part of a binary pair. And I think most stars are found as part of a system. Our sun is a little unusual in that it's not. But as we gain information, there are an awful lot of single stars. The more massive one lives fast, dies young. There's your astronomy lesson. And as it reaches the end of its life, it goes through a giant phase where it puffs up, and matter can be transferred onto the other one. It loses a lot of its mass, and if it's not too massive, it won't blow up in a core collapse. And it becomes a white dwarf, and these guys have a common envelope evolution for a while. And then a lot of that mass is cast off, and you're left with the first star and the white dwarf that's left over from the more massive star. Then the first star can go through a giant phase and transfer mass onto that white dwarf, and that triggers the explosion. And one of the things that we think is you should see a star kicked out, and that's one of the things that people look for in looking at these remnants. So to model this, you have to do a lot of stuff. You've got the lifetime of the stars themselves, and then you've got to model this accretion, and that can take place for pushing 1 billion years. And you have to have a highly specialized code that can do that long-term evolution. Then, once the matter has been transferred and the star has been compressed, it gets hot and reactions begin to go. And you can have a long period of about 1,000 years of a slow sort of simmering or smoldering. And that evolution is important because it changes the composition. And to really understand what goes into your white dwarf progenitor, you have to solve this problem. And that actually is one of the things that our group is working on. Don Wilcox did some of that work for his dissertation. It takes a special low Mach number code because you have to go for about 1,000 years, and if you capture sound waves, you can't do that. Then you have the ignition and the explosion. The remnant blows up, and eventually you have to model the light curve, and that requires multi-group, non-local thermal equilibrium radiation transport to do, and that's a complicated problem as well. So what I'm going to focus on in our research today is the explosion, how you resolve what's going on in that, and then transfer that to calculating the light curve and the spectrum of the event that you might see. Okay, that's kind of the end of the astronomy. Any questions so far? We've had some good ones. It's all crystal clear, absolutely brilliant lecture. Okay, I thought so. All right, so here's how this thing blows up. This is a two-dimensional simulation where a flame is born in the center of the white dwarf. And it's going to evolve for a while and experience what's known as a Rayleigh-Taylor instability. And that means that warm bubbles rise and mix. And then notice that it's expanding. The whole star is expanding. That rising bubble is going to transition to a detonation, the supersonic burning front. In this case, there are two of them, that destroys the star. That's the explosion mechanism that we go after. And that's not the only way to do it. But let me show you this again and illustrate a few things. In the very center of the star, it's extremely high density. And you burn without too much going on, but you're dumping energy in there. And that's going to cause the star to expand. And you see the scale is changing. This is a contour that marks the density where that transition is going to happen. So the star has puffed up and gotten a lot less dense. And then when this transition happens, these detonations, they just rapidly incinerate the star. And that's what drives the explosion. But one of the keys is that it's a dynamical problem where the density is changing. It's gravitationally stratified. It's densest in the core, and that decreases as you go up. But also, over time, it expands, and that lowers the density. The change in the density changes the nature of the nuclear burning. And in order to get what looks like a supernova, you have to have exactly this picture. And that is, the star burns for enough time that it expands, but it doesn't expand too much. So something has to trigger a quick explosion in it. And that's why we work in this deflagration, subsonic, to detonation transition picture. Because if you just whack the star and blow it up without letting it expand, you get all very heavy elements like nickel, and that's not what we see. If you let it expand all the way, it doesn't really burn. It takes that kick at the end to get it to work. And so it's a very subtle problem. And you can think of the difference between a deflagration and a detonation as sort of like a broken firecracker, right? Now, they're not legal in New York, but some of you may have seen a firecracker. If you light it, it's got a fast reacting powder wrapped up in a whole bunch of paper. The powder burns, you get a lot of expanding gas constrained by that paper, the pressures go crazy and pop. That's analogous to the detonation. It's a quick process. If you break the firecracker open and make a pile of the powder and just light it, then you get sort of a whoosh. And that's sort of like the deflagration. And you don't get an explosion in that case. You want the detonation. That's just an analogy. The physics are a little bit different. But I want to stress that it's the details of that evolution, letting the star expand a little bit and describing the burning in that process that we're after. Question?
So that green curve you showed, is that part of the model also?
So the way that model works is you specify a density at which that transition happens. And I'll come back to the physics of that. And that contour just marks that. So one of the things you could do is change that density, which represents a change in the flame speed and stuff like that, to see how it affects the results. Okay, so yeah, please.
And you're evaluating the simulation based on the spectral properties of the light that you would observe.
That's the ultimate test.
Because that tells you what the metals or whatever that you're going to find within the.
Absolutely, that's exactly right. Okay, so these things require big computers. You have to have the progenitor. As I mentioned, you've got that simmering phase. The work that Carlin did was on a so-called hybrid, where stellar evolution indicates that there's some new types of white dwarfs. And then you have to include a lot of physics. We solved the reactive Euler equations with self-gravity. I'll show that in a little bit. As I mentioned, the matter is degenerate. And then you've got a lot of nuclear physics going on. You begin by burning carbon. The white dwarf is principally composed of carbon and oxygen, and it's carbon fusion that drives it. That burns to silicon group stuff, which is a quasi-equilibrium, and then that burns to iron group stuff, which is an equilibrium. And the equilibriumness of that is important because it's an ongoing reaction that as the star expands or a bubble rises, the composition changes, and you have to capture all of that. We have to have a flame model the compact white dwarf is about the size of the Earth. When it's born, the flame is that wide. That's 10 to 12 orders of magnitude, and no dynamical simulation can capture all of that. As I mentioned, you've got that simmering phase, that's convection. The flow is turbulent. When the flame is born, that instability that I showed you, that's the Rayleigh-Taylor instability. And I'm not going to talk about it much, but you emit neutrinos, and that changes the composition and changes, it takes energy away as well. And that's very, very important, but that's the subject of another talk, because I have to go through a lot of nuclear physics. And then, as with any astrophysics problem, you have to include rotation and magnetic fields to really do it right. And Lupe will tell us all about magnetic fields before too long. So here is a plot. This is the length scale in centimeters. And we were talking about logs. It's not a logarithmic, it is a logarithmic scale where you're going through a factor of 100 between each tick. And this is the density. So over here at 10 to the 9, this is the highest density. And that carbon burning in the deflagration is something like 10 to the minus 5 centimeters. It's tiny. It's tiny, tiny, tiny. And on this plot, the dashed line indicates the radius of the white dwarf. And the solid line indicates 4 kilometers, which is about what we could resolve in a 3D simulation. So what that says is that at the high densities, which is in most of the star, almost everything is below what we could resolve. And that's going to answer the resolution question. So the first thing we do is try to understand the physics. And this is a simulation of the abundances of stuff. This is mass fraction. You can just think of it if I had a teaspoon of the material, what fraction of the mass is each element? This is distance over here on a logarithmic scale, going very small. And this is the initial condition of the flame is here, and it's propagating this way. So carbon and oxygen are our Christmas colors, red and green here. The flame is propagating this way, so it heats the material and it begins to react. Carbon in red gets consumed, and you produce, in this case, 20 neon, and then you start producing 24 magnesium. Then you consume the oxygen, and you begin to produce silicon, and then eventually you begin to produce the heavy stuff as we're going through the periodic table. Now, these little tails over here are an artifact from the initial condition where we just put a hot region in pressure equilibrium with the cold fuel and let it burn. But this gives us an idea of the structure and length scales of the flames, which are all sub-centimeter and we can't resolve. So what we're after is capturing this through a sub-grid scale model. And by that, I mean physics on a model that works below the resolution of your simulation mesh. So here's a table. I didn't put the reference, but we wrote this up in a validation chapter of the capability that we have in 3D, 2D, and a 1D steady state. And to really resolve something like that carbon deflagration at high density, to do a direct numerical simulation, meaning we're getting all of it, we can only do that in the 1D steady state condition, or case. At least with a full network that includes, like, say, the 1,000 nuclides that are involved. At lower densities, the scales got larger, as you saw. And in 1 and 2D, or in 1D, we can do a full reaction and capture the nuclear physics robustly. However, we don't want simple things. We want transients and we want a whole star. And we can do those with reduced networks, but you notice we can't get everything in one simulation. So the tiniest scales we can do right, the full star is what we want. So now we jump into the physics. So this is nap time for those who don't like physics, but the Rayleigh-Taylor instability is our friend. Imagine that you have a dense fluid, and in the case of the white dwarf, that's cold carbon and oxygen fuel over a light fluid. That's this burn material that's in this hot nuclear statistical equilibrium, and gravity is pulling down. Now the same physics influences like the supercell thunderstorms. You've got a rising warm thing that goes way up. The first thing we can do is try to resolve this with an adaptive mesh. And so here's a simulation that shows that. Each little block here is an 8x8 region of the domain, and the mesh adapts to put more of them where you have features. You see how it's tracking these plumes coming down and stuff like that. So the code that I use is the Flash code, and I should have thrown a slide in there, but I'll just say I can tell you about it. It's available if you want to play with it. It has this mesh adaptivity. The other codes we use, Maestro and Castro, sit on the AMR-X adaptive mesh framework, and those are all available for a lot of applications. That allows you to track the features that you want, but that still doesn't get you all the resolution that you need. Now, at the same time, let's look at this one more time and imagine that this is the burning case. So you've got an actual flame here reacting between these two. So initially it's a fairly smooth thing, but then the spikes begin to descend and the bubbles rise. And it increases, in this case it's a length, but in 3D it's an area, that the hot fuel is exposed, or the hot ash is exposed to the cold fuel. So what's that going to do to the burning rate? If I change the area so that I'm heating up more fuel, how's that going to change the burning rate? It's going to speed it up, that's right. So, as I showed you in that first simulation, you've got the Rayleigh-Taylor going on in the white dwarf, and this is a schematic of that, and it's boosting the burning along there. And we want to be able to capture that on the scales that we can. So AMR makes progress in that. We can capture some of those features, but we need to do a little bit more. So we look, question?
Yeah, so are you using level set or volume fluid to track the interface?
In that simulation, I just let it do what it wanted to. It was just a pure Euler area. But you anticipated the next step, and that is we've got a scheme to track that and see how it goes. So let's look at the flame physics a little bit more, and I'll come back. I'm going to go through the model. These are two simulations. In this case, it's a model flame, but they represent the physical flame. It's just a flame burning through a channel, and this is an isosurface that marks where the reaction is actually going on. Okay. In this case, the flame speed that you specify for the simulation is 1 × 10⁶ centimeters per second. And in this case, it's 2 × 10⁶ centimeters per second. And what happens is, if it's slower, relatively speaking, you've got more time for that instability to grow, so you get a larger surface area. If it's faster, you burn away the small scale structure, that's fire polishing, so you don't get as much area. But in both cases, in this case you get twice the area as you do over here. But in both cases you wind up with the same burning rate. You've got twice the flame speed and half the area. Half the flame speed and twice the area. And so the flame is self-regulated. And we can do a basic simulation of that, where this is the flame speed that you specify versus the effective flame speed. And while it's in that region where the Rayleigh-Taylor instability grows, it gives you the same result. And this is the specified flame speed and the observed, measuring just the amount of fuel that's consumed. And it turns out that that net flame speed scales as the Atwood number, which is the difference in the densities over the sum, times the acceleration due to gravity times the length, the square root of that. And so that's a scaling law that gives us the speed of a flame. Now, I think, let me just look, I think I didn't show a slide that I wanted to, so actually, let's go back. Let me just, where did my slide go? Yeah, I wanted to show, no, not there, where is it? may turn up. I shouldn't make an adjustment right before the talk, but I just wanted to illustrate this. These are Mike Zingali ran this. These are 3 simulations of a resolved flame. At the highest density, the flame speed is faster. You get a very smooth, well-defined flame. But as the flame speed slows down as you go to lower densities, you get more of this Rayleigh-Taylor. And that's the physics of this turbulent combustion that we're seeing. Okay. So I mentioned that the interior, besides the flame, but from the simmering phase is turbulent. And we did a lot of work in looking at how turbulence affects the flame. And this is a flame front propagating into a pair of co-rotating vortices, actually, yeah, like this. And as you can see, that stretches the flame front and boosts the flame. And I had a student, Aaron Jackson, explore a subgrid scale turbulence model, where these are 2 simulations where the flame was boosted in one case, and you can see it's burning more area. So what I want you to get out of that, and we're kind of getting close to being done with the physics there, is that there's this Rayleigh-Taylor instability and there's turbulence that are on scales you can't resolve because the flame is too thin, even with AMR. And so what we want is the model. So Aaron came up with a model that would calculate the enhancement to the flame. It would calculate a flame speed based on the strength of the background turbulence. And we saw that scaling law. Oops. We saw that scaling law from Alexei Koklov that gives you a self-regulated flame speed as a function of the local conditions. So we put that together. Now, Jim, you asked me about the equations we saw. So the hydrodynamics is based on the Euler Equations, and if you don't know what those are, these are the Euler Equations. They were originally written down in a very different form by Leonhard Euler in something like 1757. It expresses conservation of material or continuity, conservation of momentum, and conservation of energy. And you'll not see an explicit viscosity in there. If there were viscosity, it would be Navier-Stokes, but these assume that the material is inviscid, which is not a bad assumption for a star. It's an extremely high Reynolds number for those who know what that means. We close the system with an equation of state describing the material. We solve the Poisson equation to get self-gravity, and I'll just say that this is a hyperbolic solve, this is an elliptic. You have to make the 2 work in the same simulation. And the flash code can also advect a scalar, meaning that this is, you can think of as the mass fraction again, just times the density. That's the fraction of some material that's in there. So you can describe the flow of individual variables. And we're going to put all that together into our flame model. So here is the flame model. It's a thick flame. It's not a thickened flame. That's a distinction that the engineers will know, but I should say it's a model flame, right? Change that word to model. And it's based on an advection reaction diffusion equation that was originally proposed by Alexei Koklov, where the flame is forced to be 4 computational zones wide. Remember we talked about the grid. The flame speed is an input parameter to the model, and we give it an input flame speed from the maximum of a laminar calculation, which, well, I won't go all the way back, but if you remember that one flame that I showed that was burning across, and I said the Christmas colors, there goes, you can measure that flame speed and make a table on it. That's the laminar flame speed, just a one-dimensional flame. Or it takes the flame speed based on these subgrid models. So we take the laminar flame speed from a direct numerical simulation of a one-dimensional flame. The subgrid model accounts for that unresolved Rayleigh-Taylor instability, that square root of AGL, or the turbulence model. And you describe the energetics, the amount of energy that it releases based on previous calculations. The detonation is described by a thermally activated burning scheme that has been studied. And as I mentioned, that iron group stuff in NSE ash is dynamic, and Ivo Zeidenthal did a calculation of the equilibrium for that, and we used that to inform the changing ash. So the model looks like this. You have an advection diffusion reaction scheme where the phi is a reaction progress variable, and it goes from 0 to 1 to mark where you're either unburned or burned. The reaction and diffusion coefficients are set to produce the input flame speed. And so you handed the flame speed from that scaling law, from the laminar, from the turbulence model. And you handle the reaction with what we chose was the shifted KPP, where KP and P are Kolmogorov, Ostrovsky, and I want to be sure to get this right. Pishkanov, is that right? Anyway, 3 Russian guys, and it actually comes out of a biological application. And we found that this thing is fairly noise-free. If you just use a top hat, there's a certain reaction going on at a constant. It makes a lot of noise. And Natasha Vladimirova did a lot of work in verifying that. So here is a reaction progress variable. This is your spatial district, or your spatial domain. There's a nose where conduction propagates heat out. Once you hit a certain, this is, well, physically, conduction is propagating heat out. This is the diffusion of that scalar from the ADR scheme. Once you reach a certain point, the reaction turns on in this region, and then once it's burned, it's not. So you go from 0 to 1 to describe your flame. That describes, say, the consumption of carbon. Now, over here, the flame is burning this way. Carbon and oxygen are Christmas colors again. The consumption there in the first scalar of that ADR scheme produces about 50% of the energy of the burn. The consumption of stuff that's roughly equivalent to magnesium-24 produces about 50% of the burn as you go into silicon. And then over here in NSE, that has about 50% of the energy. All right, so who's going to ask me, wait a minute, how'd you get 150%? The answer is, again, the NSE is a dynamic equilibrium. It can be stuff in the form of iron group, or it can be nuclei broken up into helium nuclei and a lot of photons. And it just depends on the conditions. So as you have a rising bubble, it changes and it can release enough energy that's on the order of the rest of the reactions. Okay, so Jim, that was the flame model. It's not a level set, it's this ADR scheme. There is a nose, but you turn on the reaction in some form. Does that sort of answer what you were after?
Yeah. Another question, how large is diffusion, and how is the diffusion coefficient determined?
So the diffusion and the reaction coefficient are picked to match the input flame speed. It's not a physical diffusion. It's just a model. Okay, so now we've described the energy release and these scalars, but what we want to do is get detailed abundances out of that. So the flame model estimates the energy release and average composition. It's in a hydrodynamics code, so you get the temperature out of it. But how do you calculate the detailed yields that we want to make the spectrum? And the answer is that we post-process density and temperature histories of Lagrangian tracers with a detailed network, and this turns out to be hard too, because your flame doesn't capture the right scales. So for those who don't know, a Lagrange tracer particle is an imaginary construction where, well, it's a mathematical construction. You have a point representing a piece of fluid that's free to flow around in your hydrodynamics. And you can think of it as a leaf on the surface of a stream. It just goes where the flow does. If you imagine that this leaf in our star goes through the flame, the temperature and density are going to change, and you record that for the leaf all through the simulation. And then you can integrate that with a very detailed reaction network after the fact to get the detailed abundances. But even that is hard. And so we, mostly my colleague Dean Townsley, whose name has turned up quite a bit, did a considerable bit of work on this. So this is the simulation time where one of those tracer particles went through the flame. These are the reaction progress variables. That's the carbon, the reaction diffusion, and then this is the quasi-equilibrium. And you can see that it has a fairly, it's got some bumps in it, there's some features, but it's fairly smooth. This is the temperature that produced as it went, the tracer particle went through the flame. But he was able to reconstruct that with a detailed calculation of what that interface should look like if you could resolve it, and then boost the temperature and sharpen the reaction accordingly. And so when we do a supernova simulation, they have all these particles. You integrate all of them, you wind up with a final abundance, and that's what you consider is in your expanding thing that expands and cools and continues to revolve. That gets to your early remnant. So, I've got 2 minutes and I'm going to finish on time. We have this flame model that describes the bulk energetics. We post-process these Lagrange tracers to get the density and temperature histories and get, that have density and temperature histories and get the detailed abundances out of it. And from that, we can get the yield of hundreds of nuclides that are synthesized in this explosion. And with that, we can put it all back together into a spectrum. And this is, the scale is going the other way, but this has the same overall look as that one that I showed you at the very beginning, where this is wavelength along here getting larger, and you see certain bumps representing features. And these are so-called knockout spectra, and this was in Broxton Miles's paper a couple of years ago, where you could calculate the radiation transfer problem of light going through this expanding thing and interacting with the opacity of all these elements, carbon, oxygen, magnesium, blah, blah, blah. And you can just turn off one of the opacities and see how it changes. So the different colors represent features that are explained by certain elements. And the overall spectrum is the solid black curve along here. And this actually matches pretty well to the observations. Okay, so that's putting it all together. The short summary is we can't resolve everything. We have mesh adaptivity that lets us get an improved situation to capturing things like the Rayleigh-Taylor instability. It's still on smaller scales, so we have subgrid scale models that inform the flame speeds that go into this advection diffusion reaction scheme to describe the burning. That gets the bulk properties of the burning. To get the details, you have Lagrange tracer particles in the simulations that you subsequently integrate with the detailed network, and you can do that problem, and then you tie it together with a radiation transfer code to get a spectrum. Okay, what I said. And with that, I think I'm just on time. Thank you.
Do you use finite difference methods to solve Euler?
So it's a finite volume method. It's the PPM method, piecewise parabolic method, where you, you know that, yeah.
And the particles, Lagrange particles, those are passive particles.
Right. They just cruise with the flow. And so if you think about, you know, if here's a piece of fluid and the flame goes by, you just, for that little bit, you have the density and temperature history, and then you can integrate that with a detailed reaction network.
Maybe a stupid question, but so are you, the model you're using, is it a fluid model or is it an individual particle?
So it's a hydrodynamics model. It's a
Okay,
fluid
so it's all continuous.
Yeah, it's all continuous. And the nice thing about stars is there are no boundary conditions you have to work on. It's just held together by gravity.
And how do you trace then the change in, like, in the composition? Like, going from helium to magnesium and whatever. Yeah.
So there are two ways that you could do it. In our flame model, the average atomic mass is set by those reaction progress variables. You don't know what the detailed composition is, but
Just have an average
yes,
mass.
I mean, it's all done by the binding energy. You start out with the binding energy of carbon and oxygen, and you change it through fusion, and so you get an average. But then, if you go back to like that one-dimensional thing or the detailed networks, you can actually calculate and include all the nuclides that are involved. It's not like chemistry where there's tens of thousands, but with about 1,000 nuclides in the network, you can cover everything you want. So you can do the direct simulation, and that's what you do with the Lagrange tracer particles. So the flame model gets you the bulk change in binding energy of the material, and then the detailed calculation gets the actual compositions corresponding. And we spend a lot of time making sure that those are fairly consistent.
How long does such a simulation, I mean, what's the simulation time? I mean, how long does it take to such a bird start to burn? How many seconds?
So
And what's your time step?
I should have said that. All right. So if we go, so I just got done.
This is it
Do it again. All right, my calendar's telling us that.
Well, I'd happily do it again, but I have, my class is making presentations, and that might miss the point if I don't show up. Sorry, I got a little carried away. So this is actually slower than the physical time. That convective region suddenly gets hot enough that convection can't take the heat away and a flame is born. And this deflagration phase takes about a second. So this is a thing propagating through the core of something the size of the Earth in about a second. And then it transitions to a detonation, and in about another second, the whole thing is consumed, and then it expands from there on out.
What's the speed of sound?
What's yours?
So the speed of sound is actually pushing a fair fraction of the speed of light at those densities. It's maybe 1,000th of the speed of light or something like that. So
It's pretty subsonic, right?
well, the detonation is supersonic.
Yeah, but that thing is.
Yeah, that thing is subsonic.
What are the biggest challenges for achieving scalability in the software?
I think the Poisson solve is actually the biggest challenge, because that's an elliptic solve. And you have to communicate all the way across the grid. The formulation of the Euler Equations in this piecewise parabolic method is, it's a hyperbolic formalism, so you only have to look at local quantities, and that scales extremely well. And we, depending on whether we're doing 2D or 3D and can assume some symmetry, we have approximate Poisson solvers. We could do a direct solve, but it's pretty slow because the entire grid has to talk. So I think the biggest bottleneck is that elliptic solve. Now, having said that, the flash code that I'm describing here is a little behind the curve in terms of being developed so that like the adaptive mesh package can handle going to GPUs and stuff like that. But the AMRX package, the other codes we use, Castro and Maestro on, our group, and I wish I could take more than epsilon credit for this, but it's been an incredible amount of time to utilize the GPUs, and they show pretty good scaling there as well. Does that answer the question?
That's a related question. So you have the Poisson solver for the gravity and also the convection diffusion equation.
Right.
So in both places.
Well, but the advection diffusion equation, it's not a global solve, it's a local solve.
Do you use multigrid for the Poisson solver?
Yeah, that's one that we have. That's probably the biggest workhorse. There's for the 2D ones that I showed, there's a multipole expansion where you only keep a few terms because it's largely symmetric. But for the 3D, the multi-grid. I guess it's a W cycle that we use.
Quick follow-up. Do you get mesh imbalances?
So
Load imbalance?
the flash code sits on something called the Paramesh Adaptive Mesh Library. And that uses the Morton ordering, and when the mesh adjusts, it changes the blocks around to do the load balance. And actually, if we go back over this one more time, one of the things that makes this problem hard, right here, you're not resolving very much of the star because there's only a tiny bit of the flame. But as it burns more and more of it, so you go from only needing to resolve about 20% of your domain to resolving almost all of it as best you can. So the overall memory footprint goes through like 2 orders of magnitude during the simulation. And that one of the nice things about our code is that you can restart on larger numbers of processors as you need. So typically what we do is start out on, well, I haven't run on the GPU machines yet because the flash doesn't do that. But start out on, say, 100 processors, let it run a while, and then switch to 512 and then 1024 and keep going. Does that answer the question?
Yeah.
What is the time step?
What is the time step?
Yeah, how small is time
So
step?
the time step is about maybe less than 1/10 of a second. It's probably 21/100ths of a second or something.
So what current number I think is more meaningful?
So the current Courant time, it depends on the resolution. I can get you a number, but the answer is to get 3 seconds, you have to go through almost a million time steps.
And what is the physical time that you are targeting?
Well, that's this. So
1 second?
So about 1 second, this is slower than
I'll
physical.
go back to your previous slide. I think you got the answer to that question there. No, the one there.
Yeah.
So,
Yeah, so it's seconds, but yeah, I mean, this movie, the deflagration phase is about 1 second, the detonation is about 1 second, and then we let it go until it's freely expanding, and that's about another second.